All right, we're going to begin chapter 11, starting with space figures and cross sections. In this section, we're just going to be kind of getting an idea of what we're looking at in three-dimensional shapes. Because in this chapter, we're looking at all three-dimensional solids. We're going to be finding volume, we're going to be finding surface area. But before we do that, we kind of have to learn what are we looking at when we're looking at these shapes. So, first thing, a polyhedron. It's a space figure or three-dimensional figure whose surfaces are polygons. So when you see the word polyhedron, it's referring to a three-dimensional shape. Now, in this shape, we have three different parts. We have faces, which are the outside parts of this shape. In this case here, it's a rectangular prism. We have an edge. Edges are the sides here, corners where every face meets. So it's a segment formed by intersecting faces. And then we have the vertex, and it's a point where three or more edges intersect. So we have this here, each one is a vertex here. So let's take a look here. They're going to ask us to find how many faces, edges, and vertices. So how many vertices, edges, and faces are in this polyhedron? List them. So let's take a look. First thing, let's look at how many vertices do we have. So you can do this in any order. There's no certain order. So take a look at the vertices. Now we're going to name them. Vertices are these points. So every one that points on here is a vertex. So we have R. I'll do the top here, R, S, W, and V. Then we have U and T. So how many do we have here? We should have a total of 6. So we have 6 vertices. Now, let's take a look at the edges. Edges, these are going to be line segments. So we'll start at the top here. We'll go RS. Okay, there's our first one. Second one, we'll stay along the top here. We'll go SW. Work our way around, WV. Okay, and the last one here on the top would be RV. Now, that covers the top. Let's look at any other ones we missed. So now let's look at the bottom. We have UV going across here. We've already done VW or WV, so we have TW. Then that one here. Across the bottom back here, we have TU. So we've done the top one here, we've done these here. Now we just do these two sides here, which means we're going to have RU and we're going to have ST. Now that gives us a total of 9. We got 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have a total of 9 edges. In a second, we're going to make a relationship between all the vertices, the edges, and the faces. So the last one's going to be the face. So as we look at the faces, we have the face here, which is the top. It's kind of a parallelogram or a rectangle. So we have a rectangle here that's going to be R, S, W, V. Now, we also have the bottom face, which is also a rectangle, which is T, W, V, U. That covers the top and the bottom down here. We have now the back side here, which would also be a rectangle. That's going to be S, T, U, and R. And then we have two other faces here that we have the front and the back here, which is going to be a triangle shape. So we have triangle R, U, V. And then we'll start with the back here. We got triangle S, T, W. So that gives us a total of, should be 5. So we've got 6 vertices, 9 edges, and 5 faces. When they ask you to list them, they're going to ask you to list all the different types they are. So let's keep moving. Now, Leonhard Euler, a Swiss mathematician, discovered a relationship among the number of faces, vertices, and edges of any polyhedron. Now he's known for a lot of things. This is just one of them. And he came up with an equation, his formula here, to discover a relationship between all of these faces, vertices, and edges. And he found out that the sum of the number of faces, F, and vertices, V, of a polyhedron is 2 more than the number of edges. So we have faces plus vertices equals edges plus 2. So make sure you write this down. And so for any one of our shapes, we can go back and look and see what we got. So if we go back to our last one we looked at, we have 6 vertices, 9 edges, and 5 faces. So we can take these numbers here. We can take the number of faces, which was 5, plus the number of vertices, which was 6, should equal the number of edges, which we said was 9, plus 2. 5 plus 6 is 11. 9 plus 2 is 11. So therefore, both sides are equal. Now, let's take this to another shape. For the polyhedron, use Euler's formula to find the missing number. Now, in this case, you don't have to count all this. They've given you the number of faces. We're looking for the faces. They've given you edges and vertices. So what we'll do is we'll take our formula, which is faces plus vertices equals edges plus 2. And it's just a matter of solving for the missing variable. We got faces, which we're looking for. Vertices is 20, and edges is 30 plus 2. So this gives us 32 equal to F plus 20. Subtract 20. That leaves us with the number of faces to be 12. So no matter what numbers they give you, you're going to plug them in. You're going to have one number missing and just solve for that number. All right, so let's go to the next one. For the polyhedron, use Euler's formula to find the missing number. We have 20 faces, we have blank number of edges, and we have 12 vertices. So I want you to find the number of edges. So pause your video, come back when you're done. So if you notice here, we've got the same numbers we ended up using last time. We have 20 faces, we have 12 vertices, edges plus 2, that gives us 32. Subtract the 2 and get edges is equal to 30. All right, now for a two-dimensional shape, Euler's formula can be reduced down from faces plus vertices equals edges plus 1. So that means if we took our shape and from a three-dimensional made it a two-dimensional by unfolding it, this formula would be our new relationship. So it's like taking apart a cardboard box and laying it down flat. So how can you verify that Euler's formula F plus V equals edges plus 2 for the solid? So let's take a look at each part. We got 6 faces, we have 8 vertices, and we have 12 edges. So if we went through and counted them, these are the numbers we come up with. 6 faces, front and back, left and right here. We have top and bottom. Vertices, just count, you can get 1, 2, 3, 4 here, so that means we got a same on the back, 8 vertices. Of course, in edges, you just have to count them up, and it gives us 12. So how do you verify it? Well, we plug it into our equation. So we have faces is 6 plus vertices 8 is equal to 12 plus 2. Gives us 14 equal to 14, so there we verified it does work. So now let's take a look at what happens if we unfolded this picture. So we're supposed to draw a net. Your net should look something like this. Okay? Now, take this apart, you get this part here. So we've got the front and the back here unfolded. We have the right side right here, we have the left side right here, and then we have the top right here. So there's our net. So how can we verify that this shape has this formula? Well, we need to identify all of our missing parts. So let's start here with, got to find the number of faces, number of vertices, and number of edges. Now, would our faces have changed? No, we've unfolded it. The faces should not have changed, so that still should remain to be 6. So should our vertices change? And this is going to be a yes, because now we're meeting at one point. Now we've unfolded them. They've created 2 different vertices. So we need to go through and count them. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So that gives us 14 vertices. And now we have edges. I've got 1, 2, 3, and 4, 5, 6, 7. Then I have 8, 9, 10, 11, 12, 13, 14, and 15, 16, 17, 18, and 19. So we have 19 edges. So now if we plug this into our new equation, 6 plus vertices of 14 equals edges 19 plus 1. 6 plus 14 is 20 equals to 19 plus 1. So once again, why would this change? Well, it's because we've unfolded it, and where these 2 edges would normally touch, they've created, instead of being 1 edge, now we have 2. So our numbers have all changed. Now, cross-section. Cross-section is the intersection of a solid and a plane. So taking a sheet of paper and cutting through a 3-dimensional object. In this cross-section, when this plane intersects the triangular prism, it's going to break it apart, and the cross-section is the shape of a triangle. So basically think about this. If you were to cut this right where this red line is and pull it apart and looked at the ends where it was cut, the shape is the shape of the cross-section, whatever shape remains. So in this case, it would be a triangle still. Now, what if we cut it this way? So what if I took a line, and let's say I take and cut it through here. Cut this plane horizontally, so it comes through here, and everywhere I'm drawing a line here is where it would intersect this prism at. So what shape would you have here? And you should come up with a rectangle. It is a rectangular shape. So if you took the top and the bottom, pull them apart where this line was cut, then this would be a rectangular shape. So when they ask what is a cross section, it's imagine you cutting it and pulling it apart, and whatever shape remains on it is the shape of the cross section. So for this cross section to the right, what is the cross section formed by each of the following planes? A horizontal plane. So horizontal plane means it's going to cut this going like so. Now, if you cut this thing this way, it's going to look, kind of draw it here. And what shape does this appear to be? If you're cutting it along horizontally, it's going to be a circle. So what do you think would happen when we do a vertical plane? Vertical plane means we're going to cut it down and divides us all in half. So since it's easier to look at it this way than cutting down here, we're going to cut it through here. So if we came across with a plane, cut it right down the middle, it would cut here and split this in half. So what shape would this be? This would be a trapezoid. In fact, because these lines here going this way, would cut across here. This would be your shape, and therefore you'd have, and in fact it would be an isosceles trapezoid. If this was a right cone, these two sides would be the same, and we'd have an isosceles trapezoid. So, I want you guys to try this next one. Draw a cross section formed by a vertical plane intersecting the front and right faces of the cube. what shape is the cross section? Pause the video, try it, and come back to see if you got it correct. All right, so let's see here. If we were to cut this across here, across the front face and the right face, then it would cut across here and it would go straight down, cut across here, go directly over, and this is where the slice would be made. Now, what shape would this be? Well, imagine if you took this corner off and looked at it directly, it would be a rectangle. Now I realize that you may be thinking this is forming a triangle here, but we're looking at what is looked at if you took this piece off and looked directly down on it. Okay, this would be a rectangular shape. And it doesn't matter if we drew it from this point to over here, it's still going to be a rectangular shape. So you could cut it at many different locations. You could cut it anywhere on the front face all the way over to this part here, and it's still going to form a rectangle. Okay, that shape is a rectangle. All right, so this concludes lesson 11.1.